about when you get a primary, secondary sources, and we discussed extensively on advanced mineral processing slide side, saying that we can able to maximize the liberation as much as possible, and that we can do it by integrating grinding as well as a mineral liberation assessment at every stage before you proceed for the separations. So now the moment you liberate the particle, now within the particulate system, if you try and look at it, you may not able to see the particles of, though it's a mixture, but some, let's say if I take about the high density, okay, high density component compared to low density silica, aluminum silicates, then obviously there is a natural density difference. Now when you have that, each particle liberated and unliberated will have a different density behavior, and also you have a size distribution. So when you have a size distribution as well as a different density components, and we call that system called multi-component. Component means for me is a density wise mostly, but size variation also there, which you can observe simultaneously, which you cannot avoid. So that's where performance of multi-component particulate system in mineral separators. And our focus here as part of my talk, I want to see how the mechanism of this multi-component particle gets separated under the centrifugal separators or under the semi-gravity and centrifugal separator, because most of, except the flotation, which works on based on surface behavior or surface forces, most of the gravity separations work based on the centrifugal and semi-centrifugal and gravity separation. So looking at that angle, I think that's what the slides that I'm rolling on it. So anyway, this is my research, what we do it at IIT Hyderabad. So we talk about a lot of, but otherwise today's focus that I'm going to show on this. So what is it? The new multi-component classification model that we developed based on the understanding of the particle behavior in the centrifugal separator such as hydrocyclone, which will be used after grinding to separate the unground particle back into the mills, and the ground particle you send it to separation. So then that's the first part. Then the second one, dense medium cyclone, also that we can see how individual density particles in a dense medium separator, like for example lithium as one of the critical mineral, the inevitable separation if it is processed through primary ore process is a dense medium separation. That's even Dr. T. Srinivas also mentioned the same thing. So that we can also look at it. And then the third part is also we have a spiral concentrator, which you can also use for the intermediate size particle, or some extent if the high density particles are there, then you can also use up to 300 to 50 micron or even below. So these are the three I will be focusing, and then we see how we can actually understand the separation mechanism. Thereby we can able to maximize the separation between the valuable and invaluable materials. So going on to hydrocyclones, I think I don't have to give much introduction, but otherwise these are the centrifugal sedimenting devices. So that means separation happens based on the primary size, but also do the density plays a major role. So that means theoretically, if you see, if you have a coarser particle compared to fine, coarser particle will have a large mass, and then large mass attracts a higher centrifugal force, which will be settling towards the wall region, and then they slide down to the underflow. But if the particle size is small, mass is also small and then goes up. What about the same size variation is available, but the density also is happening? Then the heavier one would attract the more mass, they would also come down. And but interestingly, what happens if the size of the particle is small, the density is high, that particle also experiences higher mass. Then those particles, theoretically, they're supposed to go to overflow as per the size separation, but they are reporting as the misplacement particle to the underflow concentrate. So those losses we should minimize. And how do we minimize? So our philosophy is, until you understand the inside segregation phenomena, you may not be able to do anything. Otherwise, it becomes a trial and error approach where we may not have any control about how to do it. So that is where we go on it. And challenges is required, achieving the required separation of the this thing. And also no information on the components during the interaction is available in the literature. So recently only our group, one of our PhD graduate, Mandakini, she has done a lot of work on that. I think I'm taking those contents here to do. And also significant fraction of the misplacement of these the smaller size but heavy density are coming to the underflow. So those we are going to look at it, and we'll be focusing on three aspects. As I said, hydrocyclone, dense medium cyclone, and also spiral concentrator. So now the same phenomena is true in all the three of them, because in dense media and hydrocyclone, the mechanism in terms of the forces that are acting on a particle are very similar, except you have an additional media. Whereas in the spiral concentrator, again, it's a centrifugal, but also the gravity force that are there. But compared to these two, centrifugal forces are less comparable with respect to spiral concentrator. But they are good at in terms of separating in the thin layer of the liquid, and then you can able to get a particle segregation correctly. Now, going on to multi-component, I think this is where the integration of mineralogy with respect to your grinding has to be looked at. So then we know that the natural ore, when you try and reduce the size or even the secondary resources, you actually get a liberated particle of different components. And components that are interested for you might be having higher density or lighter density or intermediate density compared to water. You have to look at it how they can be separated. So that's the focus. And not only that, this is on the natural mineral that you talk about it. And also same philosophy is extended for critical minerals. But now going on to coal, where we see the dense medium cyclone, I have taken example through the coal, because coal is a very well established in terms of separation dynamics. But within that also, there is a call, let's say, in the dense medium separation, you target one gravity separation, like cut density, let's say I have about 1.4. And if the particles close to 1.4 density, see, if I take a beaker of liquid having 1.4 density, the particles having a density higher than the 1.4 will sink, and then the remaining particle less than 1.4 will float. What about 1.4 density particle? Where do they go? Theoretically, they're supposed to stay in the medium, right? Now, if I have that fraction higher and higher, my separation is not going to be effective. So that is where we try and define called near gravity mass fraction in the given coal. And near gravity, instead of defining exact cut density, we try and take about plus or minus 10% of the cut density. Let's say 1.4. Now I will use the range between 1.3 to 1.5, 10% less, 10% higher. Then when I do that, now that fraction, if it is high, then your separation is going to be really trouble for you to make through. So this is where, if you look at one of the coal characteristics here, I think, yeah, if you look at this one, so what we see is as you go with the relative density, so I'm actually, this is called what you call the washability data. Washability data, you take a coal, you try and separate at a different densities using laboratory chemicals and plot theoretically what you can establish. So this is where we see the yield curve comes as you increase the relative density, your yield obviously increases, and your ash curve also, again, initially you have a low ash, but ash is also kind of increases as you go higher density. But now there is another curve is plot, which is called NGM curve, which is plus or minus for let's say if I take 1.4, I'm now using this density range as a value to calculate how much of the mass fraction is available. Now, if you try and look at it, you see NGM is maximum here when you go about 1.57, 1.58. That means now separation at this density is going to be significantly very difficult, and not only there but also everywhere. So now the NGM will make a lot of separation difficulty for the dense medium process. So what we wanted is, can we also understand how this NGM fraction, if it is high in the dense medium cyclone, would affect it experimentally? So that is what the focus that we are going to look at it. And you can see now the efficiency for NGM side, it very clearly says that if NGM is let's say 75% NGM, your efficiency significantly drops. But even theoretical also, your efficiency significantly drops as you increase the near gravity material. So now with that, I think as a background, we can now move on and look at one by one. So motivation for this is basically there is a lot of data that is not available seriously. And also when you go for higher NGM and also multi-density, multi-component particle, your settling behavior also uh, inferred by the or rendered by the neighboring particle. So then those things also we should look at it, and when you go for separation of it. So this is where I think I'll take you through certain fundamental aspects which are very important when you go and understand the mechanism, especially for finer particle, like in case of hydrocyclones or even to the extent viral treating about a very fine particle. the particles of a settling velocities and rheological behavior is important, which we always see that disconnected way. But otherwise, in real separation, your particles are not single particle; they are multiple particles. And then, when the particles are consisting very fine fraction, your rheology also gets significantly affected. Now, in the literature for the last 150 years or 30 years, there is a tremendous data on assuming the density of the available mixture components are uniform. But when you have a relative density, like higher and less, now how does this rheology would affect it? That's a new insight we are trying to bring from experimental data to understand. And second is when you utilizing them, can we also, because everything we cannot measure it experimentally, which is difficult. For example, even in centrifugal separators, if the particles are segregating radially based on a size and density, we can't see anything. We only assume theoretically, but theoretical estimations are always far away from the reality. Now, can we utilize some of these computational tools like a CFD, computational fluid dynamics, actually predicts this behavior reasonably well. And also we want to do the experimental findings, like for example, tomography as well as the PEPT, positron emission particle tracking. This is like a PEPT is nothing but PET scanner. Like when you go and get a CT scan, so at 360 degrees orientation, it actually emits the gamma ray and then detects the emission based on how much of the attenuation that happens. So same principle we use it, but for tensimeter cyclone we do. And then go on bicomponent and chromite particles in the separations through CFD as well as exomites. I think both are then are being attempted. So first part, hydrocyclones, let us look at it. So this is our test rig that what we have it here in IIT Hyderabad. It's about a 3-inch and 4-inch hydrocyclone. You can do it, and very steady state you can able to attain after a couple of 5 to 10 minutes running this. So now, if you look at that, I think these are the various samples that we targeted to do it. One is to understand any process, directly jumping on your real ore is a problematic, because you may not able to sense what is happening. And it has even we see that the particles are liberated, but 100% liberated particles are there, partially liberated particles are there, even partiality that can go starting from 90 to even 0%. That means each particle behave as a different density. Now, such a complex phenomena at a time you may not able to grasp and understand. So what we have done is, can we take artificial mixture, let's say magnetite and silica, quite easily separable by magnetic separations, and you can get a 98% recovery of the magnetite after the separation. So we have taken that, and we use the Davis tube and magnet based separation to have a 98% recovery, particle size analysis, and also density determination using pycnometer. Then we have also extended this for iron ore slimes and coal. So you can see now iron ore slimes also, after you get a product, you should also get out the size distribution and density by component distribution also by using cyclosizer. So we use a cyclosizer and volumetric analysis, ICP, OES, and also particle size analyzer. And coal also you can do it sink and float as well as particle size analysis based on what you can able to do it. So this work is published. You can able to see in the one of these journal, Separation Purification Technology. And then in that, I think the way we do it, once you feed the component mixture, then you get a overflow, underflow, you collect all of this. Basically, you get a standard practice of classification experiments, and you get a products dry up and make the size distribution, also component separation. And once you get it, so you try and estimate how these variations will be there. So when you try and compare, understand the mechanism, we actually try and minimize the size variation between the two components. So if you look at the graph on the right top up, there it shows that the silica and magnetite, they are fairly near size distribution. They are not significantly varying. And then we can actually, using the similar size distribution but having a different density, it gives us some scope for understanding the bicomponent or multi-component. So now this is where we try and calculate your separation performance of the hydrocyclone, where we get a efficiency curve. So basically this efficiency curve indicates you that this is what the actual efficiency curve that you can get it, where you have some mass that automatically recovered to underflow by the water. That means those particles are not subjected for centrifugal separation. And this is actual efficiency curve, and we define the cut size. And after you take out the RF value out of it, so then we also get the corrected efficiency curve, and as a sigmoid shape that S-shaped curve that you get it. And for us, the EC value is important at every size, and also cut size for that is also important, where we use D50 size, and also slope of this curve is alpha. So this is how mathematically your data curation can be converted into performance indices clearly. So now once you go and see what happens in the bike component, and this is, I think there's an image, something skewed, but forget about it. So now if we try and do it, so when I conducted the experiments, I mean with respect to our laboratory hydrocyclone, you see pure magnetite is a green color, and the red one here is a pure silica. So these curves, other curves, let's forget it. Now when you are conducting these pure component, heavier component, actually recovery point of view is not very efficient, but the maximum recovery to the underflow comes it, okay, quite quick. And then whereas silica, there is also some fish hook phenomena that happens. That means even though some of the fine particles supposed to go to overflow, but they are also getting trapped into the underflow. That is on the pure component. Now, these are well established. If you look at last 60, 70 years of research on hydrocyclones, well understood in respect to pure component or average density. But if you have a proportionate, like let's say, if you vary the components, magnetite slowly, if I am increasing it, now what happens? You see the curve that is actually significantly shifts differently. And that is what, this is where the comparison of silica component in the mixture. So when you have a silica mixed with the different proportion of the magnetite, now the efficiency significantly shifts right side. That means now earlier, when you assume the calculated the cut size for pure silica, that is like somewhere about a 12 or 10, now that has been shifted to significantly larger cut size. That means now when you have a two component, heavy and lighter, lighter component is getting shifted significantly because of the interference of the heavy component. Now performance, if we go by those previous understanding information based on a single component behavior, you actually get a different level of information. So then your design of the operation, that you cannot go with the single component at all. You have to go by multi-component. So that is one. And we have also attempted for iron ore slimes. Slimes are again similar to what we talk about the secondary resources we do. So here also you can see overall efficiency curve that we get it here. But most of the people, they try and use this value, cut size for and the slope of this information for design operation. But actually, if you look at iron recovery, they are very different than the silica. That means if you target for iron maximum recovery, your design of the operation should be targeted by component behavior of the iron, not the mixture, which is the average density behavior. So that actually is the first time that we, I mean, it was occasionally reported, but there is no systematic of how proportion, if we try and change it, would get affected. Experimentally, we found that part. Now, that is where you can see the mixture cut size is very different than the component cut sizes. And you have to see that. And now these things we have also extended for the solids recovery also. So if you try and look at it, we assume that the solids recovery is also going to be straightforward. No, your solids recovery to the underflow, you see, it actually decreases for silica component, lighter density, a lot more compared to what it happens in the mixture. So that means now there is a lot of interference by heavier particle on a lighter component is happening. Now, I think so the efficiency and all of this that we can look at it, but I think these things we can also find it in the published literature. Now, as I said, there is also the hindrance that happens because of the fundamental interaction between the two components. So we attempted for settling behavior, simple, you take a sedimentary jar and try and see how the interface of this entire particulate system moves with respect to time, and then you try and determine h by t, where a critical settling velocity is being determined. Now pure components, we know we can able to do it, but for multi-component also you see there is a significant change that is happening. And when I try and plot this different components, you can see now proportion wise, when you increase the magnetite proportion, they are very different. So the pure component point of view, they settle very fast. You can see the slope is very high. The moment you have the other components changes, now you see the interference that goes differently, and this is where the silica settling and magnetite settling is affected moderately, but silica settling is very different as you increase the magnetite fraction. Okay, so that indicates that there is definite interference by heavy density component in the lighter density. And for that, I think we also looked at mathematical how to do it, and we compared with respect to the mathematical data fitting with respect to our parameter calculation calibration that we have done. That also is published in 2 journals that is being reported differently. Now, rheology also plays another role. So then we have also conducted the rheological experiments. I think this is where the 3 systems that we looked at. So combination of these, silica magnetate and silica chromite, and this is like a concentrated chromite. Okay, and when you try and look at it, we have also looked at how the shear stress versus shear rate goes on, and with increasing, like for example, only magnetite that you can able to see this way, this is the behavior. But as you reduce your magnetite content with the silica, now your shear rates also becoming very different, and shear stress, shear rate, and your viscosity also changes. For this is for chromite and silica combination, and we have also modeled that data with respect to possible mechanized rheological model. And then finally what we actually, if we use the model development, so that this model we can use in the CFD to predict your performance behavior. And also if we go and utilize multi-component model performance predictions for cyclones, you can also use that as a viscosity as a parameter rather than simple single parameter. So now after that, I think we conducted the computational CFD model for the hydrocyclones to understand much more detailed way, insightful of the cyclone separation. So first, anything that you try to do it, you have to validate. First, we validated. We could see the model predictions pretty close, and we have also understood the separation mechanism by classical equilibrium arbiter theory. So what is this equilibrium arbiter theory? I think I'll just take 1 minute time here, because that's a concept. If you understand, remaining things are quite easy. So what is this equilibrium arbiter theory? So when you subject for centrifugal separation, let's say you have a, let's say I'm taking any cross section. Now after steady state operations, what happened? We see that bigger size particle are getting settled, and then so as when you see very smaller size particle that will be coming up. So that means now each particle will take its own radius to move around. And so that's the equilibrium behavior that we assume. Now same thing, if I draw the conical section or cylindrical, now what happens is this is your central air core. I think we saw one of the video, right? And this is the air core. Now in the radial position, this is what the radial position that we talk about it, right? How they settle. Now there is also, you see the flow, one side goes downward and then other side flow goes upward because of the swirling motion. So one is outer swirling that comes, that is how here, and there is also inner swirling that comes because of the area restriction that comes. So now once you get it, so what happens, you have one stream of the flow is moving downward and other stream of the flow which is moving upward. Now between that, I think there is a locus of zero vertical velocity. We call it as a LZVV. So locus of this side, your flow is downward, this side is a flow is upward. Now equilibrium arbiter theory says that if the particle, whatever the, because of effective mass, it gets, the mass gets into accounted because of size and density together, right? Now whatever the component that is there, subjected for centrifugal forces and turbulent dispersion as well as the drag forces. Now if the particle by any chance moves this side, it actually reports to the underflow, and if the particle by any chance moves to the this side line, it reports the overflow. Now this is for the pure same density particle. Now when you have a multi-density particle, what happens? So this is what we actually predicted. So you can see now, earlier the LZVV, when you have it pure components, for example silica, this is a line here. But now when the silica is mixed with the magnetate proportion, this line of LZVV is actually shifting inside. That means now what happens? Some of the particle, as per the silica point of view, they're supposed to be here, which will be reporting to the overflow, right? For example, if the particle, when it is operated 100% silica, a particle of something represented some size will go, if it is here, will go to the overflow. But now when you have the mixture, that line of even LZV is shifted inside. That means now the particle which was located here now comes to the underflow instead of going to the overflow. So that indicates that interference of heavier component is significantly affecting lighter density particles. So that's one identification we made it. And we have also analyzed the accelerations. I think this is fundamentally I'm talking about the estimation of the force of the centrifugal forces with respect to gravity, we compare by centrifugal acceleration to gravitational force. And this is a drag force and also turbulent dispersion, all of that. I think I'm not going through these details, but I think you can find in the published papers that are listed in the below. So now, and same, I think whatever the phenomena that I suggested, can we witness something? The quantitatively is fine, but also can we visualize through the computational fluid dynamics, which is a very perfect tool for visualization. So this is what it happens. So I'll just take 1 minute here. You see a 44 micron particle. Okay, so we are talking about a 44 micron particle. If we go by A is for the pure silica. Okay, and this is I think pure silica, and then this is about a silica in the mixture. Okay, so when you try and go for it, so this is where we talk about it. If the particle is about here 44 micron is actually going downward. Now the moment when you have the mixture 50-50%, this some of the 44 micron particle, you can see they are actually taking inside path also. That means ideally for that size of the cyclone, 44 micron supposed to be coarser particle reports underflow as per the pure component. But the moment you have a mixture, now that particle 44 micron coarser one supposed to go overflow, underflow, but it is also taking a detour towards overflow. So that means some of the misplacement is happening for coarser particle to go to the overflow because of that shift in the locus of zero vertical velocity is happening. So that's a fundamental weakness that we can see, that how this size segregation happens. Not only that, we have also looked at the contours, right? You can see contours. This is a magnetite and silica, and 2.5 micron, 11 micron, 22 micron. So interestingly, anyway, the 2.5, 2.7 micron, when you go for magnetite and silica, even magnetite also comes everything to the uniformly dispersed. But the moment you go with the silica, you see now silica 2.75. In case of the A1 is about, I think I need to see the nomenclature. This is the first one, and this is 11 micron, 12 micron. Yeah. So one is with the mixture 50-50 and then the pure component, right? So then you can see when you look at the silica 11 micron is actually, in case of the magnetite, it is about it's actually going downward, and 11 micron silica goes up, but 22 micron silica is also, some of them they are coming in the downward form because the size cut density is about 11 micron. Now when you go for the changeover here, you can see now some of the particles, the earlier they were reporting here, but I think now you can able to see they are actually getting reduced. This is in the mixture form, this is a pure form. So pure form, you can see for the 11 micron particle, they are actually, most of them they are going downward, but the moment you have a mixture, they are actually also reported upward. Okay, that is one. And here even you can go for magnetite also. Pure magnetite, they are also settled very well on the sideway and then coming downward. But the moment you have about a mixture, the interference of this silica is minimal, but there is some kind of a diffusion that is also taking place for the particle to move or flow. So those informations we have also compared to understand why heavier and lighter particle interfere each other, but lighter one gets significantly affected. Now the second study that we extended is actually the dense medium separation in a dense medium cyclone. So here there is a technique that called PEPT, positron emission particle tracking. So in this, what we do is we take one of the cold particle bombarded with the radioisotope. Now that cold particle behaves as a tracer for us. Now that tracer, when you inject in the system, let's say this is a tumbling mill, for example, the same we can depict now on the dense medium cyclone. So in a tumbling mill, okay, when you go for the tracer, this tracer is such that we selected where it actually emits the gamma ray. Half-life is about roughly 8 hours. And typically within the 4, so this data that we try, so basically if we look at that tracer particle injected in the system, right, and then that emits the gamma ray back to back, but not just only one direction, but actually it emits every direction, 360 degrees. Now this is actually true data, but in that some noise data is also available. So if you try and filter the noise data, you actually get the true particle location and time. So spatial position and time change of each particle will be obtained. Now, if we try and do that, now we can track that particle during the motion, the way it happens. So now this will be scanned for about so even CT scan, if we go, they won't say that it won't be less than 45 minutes to 1 hour, depending on whatever. Now, the same we need to adopt here about 3 to 4 hours for bringing about ensembled average behavior of the particle in the system. So it's a very costly experiment, but anyway, it is possible. So once you know that, I think I can able to figure out how the particle. So now with that, I think in the previous slide, you can able to determine location and the time. Once you know the spatial coordinates and the time, now if you try and differentiate it, you get a velocity. If you go for double differentiation, you get an acceleration. So if you know the position and velocities and acceleration, you can calculate the forces that are acting on. So moving on to that, I think now what we have done is we have taken a dense media cyclone. Again, this is about a 100 mm dia, and we placed the dense media cyclone, again operated with the magnetite suspension, where we are also injecting the cold particle of our interest. And now this is the anyway diagram that we do. Now this is the cyclone that you can see, where it's like similar to our CT scanner, and we have a 360-degree scanners that are there. And now you similar to industry inclination, we have also made as a 20-degree inclination across the test string. Now so this is how we have also obtained, like where your particle, and then the particle x position, y position, z position, and time integral, you can able to do it. You can actually do a lot of mass related to your particle dynamics estimation. So now when you track that particle, you can see this is inside when they are subjected for centrifugal acceleration. So you can see each, so within the, let's say 3-4 hours time, it might have captured so many tracers. So that means it's a single tracer we injected. Now it takes through either one of the overflow, underflow, and goes back to the slurry sump. Again, the pump will pick up, the tracer will send back. So within 3-4 hours, you see this much of the data is encapsulated. So now that data, if we translate and then find out what is the frequency of a time distribution, residence time, we can also find out. And utilizing that data, you can also calculate your tangential velocity, axial velocity, and also you can look at the trajectory. Like you can see that trajectory contours also, you can go about it. So one of the tracer, we have taken heavy density cold particle bombarded with the radioisotope. And if we try and identify the path, you can see clearly that this is a heavy density in a magnetite media. Now, when you try and look at it, you see that particle is actually segregated at the wall. And all the time, whatever the loops multiple times that reports the cyclone, it clearly shows that this is how it is showing. And you can cut any slice and also look at the data. This is through experimental evidence, nothing computational. So now on that basis, we looked at the different tracers. I think the tracers that are being mentioned here are a different note. I think I'll just take you back. What was the tracers that we mentioned? You can see the tracers that we have taken. A relative density also is mentioned. So according to that data, we have gone and identified. So one of the tracer that we were very much interested to see if the particle comes within the near gravity density range for the operating medium. Now, how that particle behaves it. So anyway, the turbulence intensity also we have identified, which is a fundamental property to understand how the particle is getting affected by the local turbulence. But interestingly, the near density particles, you can see they are actually behaving quite randomly. It's like in a stationary liquid, when I take 1.4 density and the density of the particle is also 1.4, it doesn't know where to go. So it actually bounces back and forth within the medium. It doesn't go anywhere. So now that is on the stationary gravity. Now, if it is a centrifugal acceleration, maybe 50 to 100 times or even higher acceleration, still it does that behavior within the radial range. So we see that random behavior of those particles, and you can go by here. So same thing, if I look at it a vertical plane, you see these particles are getting recirculated. So that's the first time evidence we found. In fact, it was all the time speculated, saying that circulations would happen. Our question is how much that circulation would be lasting. Is it for 1 second or a millisecond or and that is what our aim to target, and we attempted that way. You can see very much. So this is for the particle which is exactly having a density closer to separation density, and then you can see circulations, and we can estimate the residence time also quite significantly high. So whereas a remaining density particle, if you try and look at it, less than 2 seconds or 3 seconds, the particle comes out of the cyclone and again goes back. But whereas these particles take longer time to exist, to come out of the product. And whereas higher density, you can see they are quite away, and then they are also following the path. So this entire slide talks about how this size effect also we can go about it. See, 0.78, 78 micron, 1.69 mm, and 3 mm. Again, size variation, but density also we varied, and those behavior also we captured. And there is a significant behavior, especially when you go for this intermediate size particles having a the very close density to the medium. You see how significantly they are recirculating and reporting everywhere in the cyclone. That means those particles are actually prone for misplacement rather than correct product separation. Now, the third part, I think how much time I have? Probably, yeah. I think looks like I have gone very speedy way. Okay, fine. We can discuss further if you have a clarifications or questions, anything that needed. So third study we attempted using spiral concentrator. So this again attempted by two PhD scholars, and aim of this work was actually to come up a new spiral design. I think when we visited the lab, there was a new spiral, right, that we designed. But before attempting the new spiral design, unless you understand the separation mechanism, you cannot attempt to modify something, right? Otherwise, it becomes a trial and error. So we don't want to go for trial and error approach. We want to go with a systematic scientific approach. So one of that attempt we made it through the CFD as well as experimental, both we have done it. So for CFD, I mean, it's a tool, right? It's a simulation tool. But I think the first any computational model that you attempt to use it, first the model should be able to predict well. And that attempt we have already made using some of these studies. And we took LD9, which is a coal separation spiral. And there is a lot of experimental data in Australia attempted. And we used that experimental data to validate our CFD model. So there was a pretty good match with that. Once we got that confidence of the validation, now we took that tool for simulating by component. For example, you have taken, again here, we looked at the coal particle. You can see now coal and quartz when you go by it here, right? So we see the coal 30 microns to again 100 micron, and particles also you can see now quartz also 30 to 100 micron. How size wise the density is different, right? Coal is 1.4, let's say average density 1.5 whatever, and the quartz is 2.65. Then when you have a two component, how the buoyancy force to gravitation force that would be affecting. When I say buoyancy force, is because of the drag that results into a different level. That is one we attempted. You can clearly see that the coal particles in terms of the influence by the gravity is actually compared to silica, they are influenced by less. Obviously, there is a mass difference and density difference. So silica would settle the bottom layers typically, and the coal would actually try and settle everywhere, including this picture. So you can also see the same notion here. For example, we take about a 75 micron, and coal 75 micron is actually segregated more or less throughout the trough zone, but heavy concentration is there mostly here and the middling zone. But whereas if you go with the silica, the width of the silica compared to the coal is less, but I think silica is more concentrating towards the inner zone, because then the spiral concentrator would get a heavy density particle fraction. That I think we have placed it here. And also we tried to compare the turbulence behavior. So that also we can see now at different water depth level, like you have a spiral having a water depth a slightly different way. Now you can see the turbulence in the outer region is very high compared to inner region. And we can also see that the free surface will have a lot of turbulence compared to the bottom layers. Bottom layers, they behave like a stream flow. But top layers, there is a recirculation that happens. Because of that, we can see that the turbulence is very high. So now utilizing this, now further we also conducted the experiments, and this is where we have done the magnetite and silica and attempted. So these zone 1 to zone 5, right? If I go back in the spiral, so at the end of this spiral, if you look at the trough section, right? This is a trough section. We divided that section into 5 zones. Zone 1 is a very inner zone, and zone 5 is actually outer zone. So zone 1 and close to zone 2 is actually your concentrate product, and middling, and then zone 5 and those are outer. So if you go and look at it, how, sorry, I think, so if you look at it here, we see zone 1 to zone 5. And we varied not just only pure components. So we have done experiment with the pure component, silica ones and magnetate ones. We can say silica 100% is just 100% of it. And magnetate is also 100%, that means pure magnetate. So we plotted, we collect, so we fabricated one sampler. It's like a similar trough profile. We are also using, what is it called? Epoxy resin. We took it, and then we made zone 1 same width, equal width basis, 5 divisions we made it. And in that we also had some volume collection of the slurry. So basically in the flow when it is coming, we actually put this and collect it. So it's like and it took a lot of time for us to figure out how much time we should expose, because you know it's like when you want to get on a train, if it is running with some speed, 50 kilometers per hour, right, from the platform. Now, what do? You cannot jump on it, right? What do? You also pick up the same momentum. So basically, you keep the same velocity compared to train, then only you can jump in and get on. Same here, we know what is the velocity of these particles that are coming and the slurry that is coming at the zone by CFD. Now, knowing that velocity, now we try and minimize the time of collection, not to have interference, but also the insertion would be the same velocity of what the slurry comes at the bottom. So that way we collected samples for all of these experiments, like pure magnetate, having a magnetate and silica different compositions. So by looking at this data, we don't get anything seriously. And students, basically, they get confused saying, sir, I'm seeing a similar S profile. What is a great science that is involved? I said, like, check the microscopic way. And then I told that, you see, zone 3, zone 2, they are different. And why they are different? Let us estimate what is the average size of each size distribution. So that's a plot now we changed. So if you try and look at it, for magnetate silica, magnetate heavy density, silica is a lighter density. Now zone 1 is a concentrate, where zone 2, 3 are middling, and then the tailings, right? The outer one. You can see very clearly the heavy density, the lighter density and heavy density, first blue color if you see, the heavy density magnetate segregates towards the concentrate and very less on the outer. But also silica, they are actually more dominant in the middling compared to concentrate or even outer zone. So this is what we tried and tried to understand where the segregation of these two different density particles is happening, and where the misplacement that is possible. So if we try and understand from this, we have also extended the further, not only this is the average size of the size distribution. So if we go further, recovery point of view, right? You can see your magnetate recovery very high compared to feed, right? Recovery is how much is recovered to the concentrate zone with respect to feed. So recovery of magnetate is high, but recovery of a silica is high in the tailings zone. So that is how we figured out. This is on operating silica separately and magnetate separately. Now, when you go with the mixture, what happens? Now that is the same recoveries would not happen for the this is the size distribution D50 size wise. I think recoveries, I have it here. We can see recoveries. What we look at it, magnetate recovery is very much high, where you can see 30-70 case, you are getting about a 70 to 80% recovery to the concentrate, but silica is less. But if you go on, this is on the recovery in the concentrate, right? So if you try and look at it, recovery in the tailings, you get a silica very high. But now, some of these cases, when you go for combination of proportions, your interference of heavy density is also happening with the lighter density here. So, for example, when you go with the 30-70, 30 is your magnetite and 70 is silica. Now you are getting a better recovery. But when the silica proportion is reduced, your magnetate interference is actually coming, and their recovery is same in the tailings. That means now misplacement of the recovery is also, sorry, misplacement of the silica component is also affected by the magnetate process if the fraction is high. So now up to here is fine. Now can you extend the real particulate system like chromite ore? We took a low grade chromite ore, we attempted the same. Now this is what one of the observations we can see. So in chromite, you have a chromite rich particle Cr2O3 and iron rich particles and silica. And we want to see the better separation of these when you try and look at it. So in the concentrate, if you look at it, your chromite recovery is effective because there is a high density. And also, unfortunately, the silica, the iron, which is supposed to be higher than the chromium particle, but the iron particles are actually matrix point of view. They are associated with the silica complex. So that means now they are actually following the silica behavior than the chromite. So that's one way it's a good news because then you can actually clearly separate the chromite and leave the iron. But in case of you go for the application of ferrochrome alloys, they wanted iron also to be recovered along with the chromite because then you get a better the yield in terms of your iron and this thing. But that is not possible for all the mineral. But we identified here saying that this is quite interfering where your iron particles are also getting affected with the presence of lighter silica. And you can also tailings, you can see the tailings for iron and the silica, they are quite high, but chromite is less. But at finer sizes, even you have a misplacement of some of the chromite particle. So this was a witness where we realized that I think if you want to get a better chromite recovery even on finer sizes, this conventional spiral design is not effective. Now we utilize the CFD to do for about more than 56 design explorations. We simulated this story through 2 PhD scholars. Finally, we got it. But that's what the component behavior. So I think with that, what I want to conclude is the performance characteristics of the multi-component particle in hydrocyclone we measured, and we realized that the heavy component affects the lighter one significantly, and component cut size and beta performance is what you call a fish hook phenomena also happens. I didn't go much in details, but I think you can find in my published papers. And separation, suspension rheology and hinder settling studies are very important. It's like the way we do for what you call the liberation mineralogy study for every mixture or every mineral. You also need to do the suspension and rheological study for every material that you process it. So I think that gives a lot of fundamental insight what is happening in the separations. And mechanism of bicomponent particle interaction during separation of hydrocyclone also investigated both experimentally and CFD. And PEPT study we have extended for NGM particles dynamics inside DMC, and we looked at the effect of NGM range density, size and feed density were studied, and notable differences on the profiles, particle residence time and relative particle segregations were observed. And spiral concentrate modeling also attempted apart from the experiments that we have done it. I think this is my team where a lot of people are involved. Otherwise, Mandakini, I think she is the one who's actually mainly contributed for this. And yeah, so I think, yeah, that's all from my end. Probably I have another 10-15 minutes. Looks like I really went very fast. Huh? But you can ask anyway. Probably we can interact sometime. So dense media cyclone. Yeah. Then we'll be using different material of different size. Yes. So the process that we have actually used, I didn't pay attention much, but otherwise, if you look at it here, right? So it's you have a magnetate, which is a medium, right? So magnetate fine powder having a specific gravity 5 is mixed some proportion with water. Let's say if you want to prepare a 1.5 density medium, now volumetrically I can calculate and mix it. So that mixture is prepared in a sump and circulated thoroughly to make it as homogeneous. Now when this is processing, and now our main study is not the medium, it's a coal particle. So we have added 1:4 ratio for coal particle volumetrically. That means if you have a slurry, let's say about a, yeah, you can pick up and talk. So if you have a slurry volume, let's say 100 liters, and about a 1/4 of the volume of a coal is being added, which is exactly industrially they practice 1:4 ratio as a coal to medium ratio. And we added the true coal particle. In that, one of the coal particle, for example, if you want to target a density of a 1.4 tracer, I have written there, right? T 1.47. And that tracer is prepared using cyclotron, like, which is like at a high velocity, the isotope is bombards with the coal particle, and that particle now encapsulate the resin inside. Now that coal particle is 1.4 density. Now that particle is being tracked about 3 to 4 hours under the CT camera or PEP scan. And after 4 hours, whatever the data that we process, right? For example, if I look at that picture, first one, that much of the data is available, number of times it appeared in the scanner. And that data we have analyzed looking at how much time, what is its effective residence time, and what is its velocity, and what is its, yeah, maybe here. Yeah. So you can see now tangential velocity, axial velocity, all the information that you can able to capture. So that way, the system is actually represents a true industrial operation, but in a laboratory condition. My cyclone is about a 4-inch, but industrial they operate about a 10-inch or 20-inch depending on it. But otherwise, the dynamics very similar to, so it's a true coal slurry that is being subjected for centrifugal separation and trace the particle. And that single particle for 4 hours, we assume that it actually goes in a ensembled average phenomena of the behavior. So then we capture that and then identify it.
In the same students, we know that how the setup of part of cyclone interprets students.
Come again?
Yes, sir. As I understood, my is like that's complicated system. Like when you are attempting to fit studies, how do you manage those complete system into that organization? Is it under process thing or it is centrally between the particles that like?
I'm not still clear about your question. Can you elaborate the question?
Sir, in your studies,
yes.
You get the sample at 8 hours.
4 hours, right. Yeah. So 4 hours, it's a continuous operation. You cannot interfere. In fact, it's a radioisotope, right? And radioisotope, when in developed countries, or I would say South Africa, I did these experiments in South Africa one of the summer. So basically, when the system is operating, it's like MRI when it is on, nobody is allowed to go nearby except the operator, which doesn't have any metal along with him, right? Same way here. And in fact, there is a myth. People will scared to go and do this radioisotope experiments in India, but many places, the amount of the radiation that you get under the sunlight, morning, let's say 9 to 11 o'clock, if it is a full bright sun, it's much less than that radiation what you get it here. But still, we try and take most of the precautions, and we don't go nearby that system at all for 4 hours. And what we have is separate DAC system tracking. You come out of the cabin and track it, unless there is a mechanical, this thing. And in fact, after the experiment, because though the half-life is about 8 hours, we conduct 4 hours. The remaining half-life still there, right? We don't want to touch the slurry. We preserve that some material as it is in the container. Next day we'll come back and destabilize entire stuff. Again, we cannot throw. We have to hand over to some vendor who collects the the waste that of that nature. So it's a full operation for 4 hours. And of course, one can question saying that's how, what about the wear and tear of the operations? Yes, the cyclone gets eroded if we operate about 15 days continuously. But for us, is 1 day, 4 hours is not a major deal. And we'll start the experiments again next day or so. So every day we only do one experiment. And if we have an interest, let's say same slurry, and if you want to add a new tracer, a different density than what was added, you can add on. But now that time what happened? You see the two densities of the particle reporting at a time. So you have to demark those. So that means you are now, a problem mathematically becomes a two density particle tracking, a multi-density particle tracking. That technique also is available, but we have extended later. But I think for our understanding, this is what we attempted. Yeah. So any further questions? So the relevance that critical minerals I am only depicting in terms of the varying density liberated means how they behave in the separation, because without a gravity separations, be it a centrifugal or a gravity, you cannot able to reject most of the gang material. So gang material being a lower density component compared to other components, I think there is a lot of advantage for us to go with the separation. And the separation mechanism, when you increase the gang mass, which is like if the particles of interest is like less than 1%, 2%, now remaining 98% is your gang. Now when you subject for, let's say, you might have seen this, right? I think I told you last time also. There is a lot of YouTube videos you can find the way they find the gold nuggets, right? They go with the river basin or lake basins. They try and put up on a shallow tray, which is a circular disc. In the center, you have a slightly depth, which is nothing but just imagine the spiral, right? The spiral that is there, they are doing manually. But here we try and do the systematically where your clear layer of a liquid of certain depth is being encapsulated. Heavy density comes very close to the center zone. And that's what we tried and looked at how silica magnetate, how much it comes. But what in those operations, whatever people with the minimal knowledge, they try and attempt it, they still lose a lot of gold. Why? Because they are not able to look at how in a bigger particle, if anything is entrapped, which you cannot do. But in this, if you grind it to the level where sufficient liberation happen, then you can able to do it. In fact, there is a major work going on, seabed mining. If you look at it, critical minerals, I think Russia is already on that job. India is now slowly pitching in through geological NGRA and GSI. But if you look at the diamonds production, right, some of the diamonds, especially the African continent coastal region, I think other side is Namibia and those areas, your diamonds are there in the under the seabed. Now, where are they hiding in the seabed? If you try and dig out anything out of the seabed, you actually see a lot of shells, right? Lots of shells variation. And these diamonds, being a heavy density, they found that they actually go into settle down core center of the shell. Okay, but then a shell is not again a single entity. You have a lot of debris got into all that. So the debates, I think when I was there in 2017 in South Africa, so they came to University of Cape Town to discuss how do we liberate this diamond-rich particle from the shells. So again, one of the target is to do the crushing, grinding, because shells are so brittle. Now, if we try and grind it, even if we go and grind it very fine also, nothing will happen to diamond grains. You can able to capture. So then essentially it becomes a multi-component. Like what is it? Shells are made of your, the calcium rich mineral, which is the density is much lower than 2.7, 2.8. And then you have other materials that might be having a different this thing. So essentially it's a subject of multi-component. And they also attempted to do one multi-component study for jigging and other thing. Basically, instead of grinding everything, we can actually try and get the maximum possibility of some scope of this diamond grains to come out if we do the this pulsation based. So that is what the operation called jigging. So they subject for jigging, and all that they had to do on the ship itself. You cannot bring anything out from the sea to the shore. So they were establishing a mobile plant. It's like the way we extract the petroleum, right, on the ship itself. And then they separate and bring the material to do downstream process of further dense medium, all of that. So it's involved multi-component in a way what we understand. But otherwise, the basics still very important for us to go and get your design choice. Otherwise, any vendor, if you say, I want this separation, there will be a dozen of vendors will line up saying that my equipment is better, my equipment better. How do you see yourself as operator? That you need to have basic knowledge of these things and selecting and identifying. All right. Okay. So if there are no questions, you have something? Okay. So we can close. I think we have Dr. Ambika who can take next lecture.